The final section of ideal gases is when we try to tackle the assumptions that we have made so far when we study ideal gases. If you remember something that we said about the ideal gases, we will mostly observe ideal behavior. That is, we will mostly observe this kind of behavior, this simple linear or inverse relationship among magnitudes for ideal gases. And what does that mean? It means that the size is negligible, the size of the molecules or particles is negligible, and also that molecules or particles do not interact with each other. So sometimes, depending on the gas or depending on the condition, so that's important to notice, depending on the kind of gas and depending on the conditions of pressure and temperature, these assumptions are not true. Okay, so these two assumptions of the size of the gas, of the size of the actual molecule, or that the very interaction among them. Okay, so let's first talk about interaction. What is the effect of interaction? So, because actually, as you probably know, if you have water or if you have ammonia, there is actually a strong interaction. There are hydrogen bonds interacting with each other. Probably you may remember the hydrogen bonds in here, right? So there's actually this assumption that they do not interact with each other may not always be true. When is that not true? Well, if we have low temperatures, or if you will, the low density or low pressure, the behavior is similar, molecules will notice each other. Why is that? Well, if they don't go very fast, as soon as molecules kind of go by close to one another, there's attraction among them. So what are the consequences of it? Well, notice that if this particle was going to go this way and suddenly feels attracted towards this other particle, it will not be impacting against this wall, and therefore the volume will be smaller. And that's the effect. At low temperatures, or if you will, at low pressures, what you see is that the volume is less than ideal. So the volume is less than predicted by PV equals nRT. It's less than ideal. Okay, so the volume that this formula gives is more than what it actually is. That is one of the consequences of treating with non-ideal gases, and specifically molecules that strongly interact with each other. That's one of the assumptions. The other assumption is size. So what does size have to do with deviation from ideality? Well, notice that as soon as molecules have a significant size, they kind of will bother each other, and this will be remarkable. This deviation from ideality will be more remarkable mostly at high temperatures. So at high temperatures, or if you will, at high pressure, you will see that molecules start bothering each other. Notice that maybe the interactions are not that important because they're going very fast. They have a lot of energy, so maybe they do not interact with each other that much. In this case, the volume will be larger because they kind of bother each other. Does that make some sense? I hope. So there you go. Because of that, then the volume is larger than what you would calculate with PV equals nRT. All right. So there's also a very graphical way to represent that, and this is what this what this graph looks like. Notice that in the y-axis you have n, and in this case we want to represent this this fraction, PV over RT, and for an ideal gas, if we're talking about 1 mole, we're talking about 1 mole. If we do this ratio at different conditions of pressure, an ideal gas, of course, would always give you 1, because that's what it's predicted. That being said, though, what we observe is that at lower pressures, molecules don't have enough velocity to escape others. They start interacting, so this is because of the interaction, and you will see a decrease of volume. All right, volume is in the numerator, therefore you have you measure volumes that are lower than 1. The measured volume is lower than the predicted one by the ideal gas law. But at higher pressures, you have the effect of size. So because of size, you will have volumes higher than the ideal. Okay, so if you will, molecule size start getting in the way and take up more space. Okay, so notice that these are, and this will result with a higher volume. These two effects are contradicting each other. So depending on the pressure, you will have a deviation from ideality towards a lower volume, and at a higher pressure, you will have a deviation from ideality resulting in a larger volume than the ideal one. Okay, the same curve can be found for different gases. Here you have methane, and notice that helium and hydrogen do not offer this kind of curve because of the interaction. That makes sense because helium and hydrogen have very weak van der Waals interactions. Probably you learned that in previous courses, that some molecules offer stronger molecular interactions, others don't. So the more sticky the molecules are, and you can imagine that water being able to form hydrogen bonds, it will have a big curve pointing in this direction. But hydrogen and helium barely interact with each other, so they do not offer this kind of deviation. Let's practice a little bit, just a couple of multiple choice questions. In this case, it says, because of the non-negligible size of molecules, okay, will volume increase or decrease compared to the ideal gas? All right, and will it happen more remarkably at high or lower pressures? Well, just if you notice here, at higher pressures, because of the size, you will see a volume increase. Okay, so you will see that the volume will increase, so it's either this one or that one. And when will it happen? At higher pressures. So the volume will increase at high pressure. Let's solve another one. If molecules start interacting and attracting each other, okay, so remember in that kind of curve, now we have to be around here. Will pressure be higher or lower than the ideal gas? Will it happen remarkably at higher or lower temperatures? Now I just changed here. Notice that this was pressure, but I can do something very similar with temperature. In this case, you have to kind of have a physical picture of what is really going on. Notice that molecules will attract each other when they're not traveling very fast. If they're traveling very fast, they will barely notice each other. All right. So the effect of attraction among molecules will have to happen at lower temperatures. All right. And because they interact with each other, they will not hit the wall as hard as they should. Does that make sense? Because they will be attracted not by the wall but by the molecules inside the wall. So this will happen at this will happen at lower temperatures, so it's either one or the other, and the result is that you end up having lower pressure. All right. It's important to have a physical understanding of these descriptions. Okay. There is, just to comment very briefly, there is one attempt to solve these problems. We will not be talking about the van der Waals equation, but van der Waals came up with a modification of the PV equals nRT that tries to solve this problem that when we have real gases, well, there's some deviation because of the size and because of the interaction. Now, notice that there's a factor adding to the pressure, and there is a factor subtracting to the volume. All right, and depending on the gas, you will have different factors. Okay, typically, let's choose one that is very sticky, right? If you want, sorry for the term sticky, interacts very strongly among molecules like hydrogen bonds. You will see when the interaction is strong, you will see this number being large. Okay, for helium and neon, for example, this interaction is not so strong. All right. Hopefully that makes some sense. We will not talk more about this. It's just that there's an experimental version of the PV equals nRT that tries to solve the actual non-ideality of gases.